Hello everyone, I'm Moen and I have Amireza right here beside me, and today we will be presenting our chemistry summative, which is about the color of gemstones. Now Amireza is going to give you some background information about the topic.
Okay, hello everyone. What is a gemstone? A gemstone is a mineral, rock, or organic material that is used for jewelry or art. A gem, such as diamond, is a type of gemstone that must be cut and polished, or even sometimes go under heat treatments for its beauty to be visible. These gemstones are valued based on their rareness and their finish, softness, and the quality of their crystal, and they are obtained from mines from all over the world.
Here are some examples of common gemstones, and as you can see, they vary immensely in their colors.
Okay, what causes the color of gemstone? The most common cause of gemstones color are transition metals that are present in their structure. Transition metals are metals in which the d orbital is being filled with electrons, and those that are in the gemstones mostly have an incomplete set of 3d electrons. In gemstones, transition metals are the most common cause of different colors. Changes in the energy of electrons of 3d orbital corresponds to the energy of visible light. When white light passes through a colored gemstone or is reflected by it, some of the energy of visible light is absorbed, causing the 3d electron in the transition metal ion to undergo an energy change. The light that is transmitted or reflected appears colors, because those colors corresponding to 3d electron energy transitions have been absorbed. Because this light is deficient in some energies, those that have been absorbed, the light appears colored. For instance, iron 2 ion produces the red color of garnet and the yellow-green color of peridots. Manganese 2 ion is responsible for the pink coloration of tourmaline, and also color 2 ion colors turquoise. Another cause of the coloration of gemstones is the intervalence transition. Intervalence transition is the electron exchange between two metal ions. In some gemstones, the color is caused not by energy change in a single transition metal ion, but by the exchange of electrons between two adjacent transition metal ions of differing oxidation states. The energy needed to transfer an electron from one ion to another corresponds to the energy of visible light. This transfer can only occur in compounds that have at least two elements in different and variable oxidation states. And as you can see here in the picture below, you can see how this process occurs. The light strikes the atom and the electron is moved from one transition metal ion to another. An example of inter-valence transition occurs in sapphire. The bulk of sapphire is alumina, as in rubies, but some adjacent pairs of aluminium ions are replaced by an iron 2 ion and a titanium ion. When light of appropriate energy strikes the crystal, energy is absorbed, and an electron moves from the iron 2 ion to titanium ion. This movement is called the intervalence transition. Another topic is Alexander effect, which is the color change in the gemstones. Some gemstones are able to change their color according to the light that are viewed under. This effect is sometimes confused with the pleochorism, where stones show different colors down in different crystal axes, such as iolite. However, true color exchange exhibits itself as a color difference over the whole stone when viewed in different light sources. Color change in garnet is part due to its even balance of transmission wavelength peaks in the green, blue, white, red spectra, which depends on light source under which the stone is viewed. As you can see here in the picture, we have on the left side the garnet that is viewed under incandescent light, and on the right side we have the garnet that is viewed under the fluorescent light. As you can see, the color is changed. Color change due to change in the color of incident light. It's important to remember that the fluorescent light is bluish, which is reached in the blue wavelengths, and the candle light is reached in the red and orange wavelengths. Alexandrite is the best known example of the gemstone that changes color depending upon the light it is viewed under. In the case of Alexandrite, there are two approximately equal-sized transmission windows, the first at the blue and the second at the red wavelength. When viewed in a light made of all wavelengths, the stone transmits blue and red and often looks purple or purple-gray. Here is a diagram showing the illumination of Alexandrite under white light. As you can see here, the illuminated light has all wavelengths, and the transmitted light from the stone looks to be purple-gray. When viewed in a light containing mostly red wavelengths, such as candlelight, the stone looks red. This is understood because although the stone could transmit blue light, there is no blue light to transmit. And here's a diagram showing the illumination of Alexandrite by reddish light. You can see here in the illuminated light, the red wavelength is more than blue and other colors. And as a result, the transmitted color light appears to be orange and red. The reverse is also true. In light rich in blue wavelengths, such as fluorescent light, the stone looks blue because although it could transmit red, there's a little red in the light to transmit. And here is a diagram showing that. You can see that the blue wavelengths are more. As a result, the transmitted light looks greenish blue. And here we have a video showing you how this can occur in a stone when the light changes. You can see here at the first the light looks green, looks green, but after the light changes, the color also changes to greenish, orangish red. Okay, from now my friend Moin continues.
Okay, another important topic that reflects the color of gemstones is impurities. Like you might have noticed, not all gemstones are pure in nature. This totally depends on a period of time that they have been trapped underground, exposed to immense amounts of heat. The gemstones that are recovered before they reach their ultimate period of excellence end up with other elements and minerals as part of their structure. This results them to reflect different colors aside their original ones. For example, some impure form of ruby might as well reflect yellow-green colors due to perioded ions in their structure. When impurities are added to colorless gemstones, brilliant colors are frequently produced. When chromium is added to colorless corundum, a red ruby is born, and a green emerald emerges when chromium is added to colorless beryl. Diamonds can also be colored blue, yellow by addition of the impurities. The question now becomes, how exactly do these impure substances alter the color? Well, this goes back to the crystal packing structures that each gemstone contains. Like you can see here, diamond contains a cubic or isometric structural packing, and a more complex gemstone such as pink tourmaline contains hexagonal ones, as you can see in this video right here. So all these structures contain holes that could be filled with specific impurities according to their shape and structures. In this 3D diagram, you can see the structure of a ruby. Ruby contains holes, like you can see here, between the elements that produces it, that could be filled with elements, so these elements could reflect other lights other than the light that the ruby itself can emit. Another important procedure for the light that the gemstone reflects is called nuclear transformation. Not all gem colors are produced by transition metals. In some gemstones, the colors are produced by the presence of foreign atoms with a different number of valence electrons than the ones they replace. These foreign atoms are called color centers. Because the replacement atoms have the wrong number of valence electrons, they can supply or receive an electron from another atom by an inter-valence transition. My friend Amir Reza explained this process, but what he didn't mention was that these color centers are often produced by nuclear transformation. An example of such a transformation is the change of radioactive carbon-14 atom in diamond into a nitrogen atom through beta particle emission. To recap over this process, for those of you who don't remember what the beta particle emission is, it's when an element known as element X right here, assuming that it's element X, with the atomic number of Z and the mass of A is transferred to and it produces the element Y, and the process takes place when a neutron is transferred to a proton. So you can see there's a +1 over here with the same atomic mass, and in the process an electron is emitted and released. So the new nitrogen atom that is being produced has one more valence electron than the carbon atom. These nitrogen atoms cause the coloration of blue and yellow diamonds. Color synthesis can be created artificially by irradiating the gems in a nuclear reactor. Many bright blue and bright yellow diamonds are produced in this manner. So another process that we included in our research is heating. Heating is the most common form and famous enhancement for the gemstones. This is so common with corundum, ruby, and sapphire. Heating can cause the color of a stone to darken, lighten, or even completely change, and can also improve gem clarity and brightness. Heating of most kind of gemstone is a standard treatment procedure, and the knowledge for it has been passed in over many generations. Heating methods vary from simply burning method to a very high complex technique and with under regulated temperature known as Vernal process. Most rough gems are heated to enhance their and improve their quality. Heating does not change the atomic structure of gems, but only modifies the sharing of electrons between crystals. This is really important to remember. So to summarize, heating can improve and alter gemstones color and create clarity. So now I have an example of a transanite, which is a gemstone, and you can see how heating affects.
What we're going to discuss today is heating of tanzanite. Now this is a natural colored tanzanite with a color known in Tanzania as diesel. Now tanzanite heating is required to remove the yellow that's in the trichroic gem and leaving just the blue and the purple. Now to do this we have to heat tanzanite to 1,000 degrees Fahrenheit. It takes about 10 hours. We'll be able to remove this and we'll see what the color of our gem is. Now here's our preformed rough piece of tanzanite once again after treatment to 1,000 degrees Fahrenheit.
These are our resources, online resources and book resources.
Thank you all for listening to our presentation, and I hope you enjoyed it and learned something about these wonderful gemstones.
Thank you.